we are gonna do another example from the PowerPoint slides. So here it is. This is example 4. Let me just read it to you first. In bees, normal wings are dominant to vestigial wings. You don't actually have to understand what vestigial wings are. Okay, it's just a particular trait, right? It means like tiny wings. Okay, but again, like it's not crucial to solving the problem. The key thing to realize here is that there are two different kinds of wings. Right? So we're gonna write down normal wings, and we're gonna have these vestigial wings. And we're gonna have to use an alphabet to represent these things. So use capital W for normal wings and little w for vestigial wings. And then we have the pollen sacs here for the bees. Deep pollen sacs are dominant to shallow pollen sacs. So we're going to put deep here, capital D, and shallow is going to be lowercase d. Right? So we have a male bee and a female bee. Let's take a look at the male bee first. Male bee. What's going on with this male bee? It has vestigial wings and shallow pollen sacs. Right? Vestigial wings and shallow pollen sacs. The question doesn't tell us whether it's heterozygous or homozygous, because vestigial wings and shallow are both recessive trait, and therefore there's only one possibility for the genotype. Okay, so this is the male B. Male B is going to be um, vestigial wings, so small w, and small d, small d. Okay, and then we're going to look at the female B. Female B is right here. Homozygous normal wings and heterozygous deep pollen sacs. What would um what would the genotype be? Can someone please tell me?
W, capital W, W,
Okay, big W, yeah.
and here capital D and small d.
Okay, so big W because it's homozygous, and heterozygous deep, so big D and small d. Very good. Now we're going to determine the possible genotypes for all the offsprings, and which means we're going to cross them, and we have to write out the gametes. Gametes. What kind of gametes can the male bee produce? Well, it's only small w and small d. There are no other possible combinations.
One.
Yeah, just one. And for the female, we can have big W, big D, and big W, small d. It would be the same with the other W, so I don't have to write it twice. Okay. If you write repeating gametes, your table is going to end up being unnecessarily big and complicated. So our Punnett square is going to be 1 by 2, but you always want to have an extra column and an extra row when you do it on the test so that you can fill it out properly, right? Okay, so we're gonna have actually we're gonna have small w, small d on the side here, and then we're gonna have capital D, WD, and capital W, lowercase d. Right? So again, this is like 1 by 2, which means you want the table to be 2 by 3. Right? Always one extra when you create a table. And then we just put the letters together. The answer would be 50% like this and 50% like that. This would be the genotype. And as for the phenotype, it will be 50%. These are normal wings. Normal wings. And deep pollen sacs. Whereas the other one is also normal wings, but shallow sacs. So the female here, someone asked why it is capital W and capital D, because the female is homozygous normal wings. Homozygous means the same letter, and normal in this case, normal is capital W. Right? That's why it is two capital W's. As for the pollen sacs, it's deep, but deep can be big D, or big D, small d. In this question specifically, it says heterozygous. Heterozygous is different as opposed to the same. Is that okay? All right. So that's the answer. Any other questions? Okay, so I'll do one with you like on the test platform, just again to show you what I expect. And you should practice this, okay? Not the question specifically, but like practice how to key it onto the answer box so that on the test it's not like the first time you're doing it, and you won't run into any trouble. So under the quiz 4, there is the practice genetic problems. And again, this is just for you to learn how to key in the answer. We already did this one last time, so here's another one. In mice, gray coat is dominant and to white coat. So first thing I'm gonna do is I'm gonna go like big G is gray coat, and which means small g is white coat. Okay, you need to let me know what letter represents what. And then long tail is dominant to short. So you can use capital T for long tail and then small t for short tail. Okay. Next, cross a mouse with heterozygous gray coat and short tail. Okay. So if you want, you can just copy it, right? Just copy it, highlight it, Control C and Control V, copy it, and then you're gonna write out the genotype. So what's the genotype of this mouse? Heterozygous gray with short tail. What are we gonna write?
Capital G, small g,
Mm-hmm.
and short small t, small
That,
t.
that's a small t, right? There's only one way to be short tail. It's homozygous. And then the other mouse is gonna be white coat and heterozygous long. So if it's white coat, is small g, and then big T, small t. Okay? These questions are 5 marks each. Okay, so like write in some details so I can give you part marks even though your answer is not correct. Okay, so then we need to have the gametes. Okay, and you can say gametes. I mean, there are different ways you can do it. Like you don't have to do it exactly like this, but looking for the information that I have here. So gametes, we can do the gametes here. What are the gametes? Well, it could be big G, small g, small t, right? That's all there is. Again, you can do it on paper first before you type it out. It's totally fine. You just gotta show me your paper, okay, when you're writing it. This is small g big T or small g small t. Okay. So our table is like it's two gametes and two gametes, so two by two. But I always, when I create a table, I have to make sure I have an um, additional row and additional column. So you see, in this case, I don't see the table icon, right? If that happens to you, you just press this list here, and then it's going to show up. Right? So I'm going to create a 3 by 3 table. Then I'm going to fill in the gametes. Big G, small t. Okay, please key it in carefully, making sure that you are not going to have the wrong case letter. And then you put them together. Okay, over here is like that. Okay? Just like you would. Okay? If you do it on the paper first, it might be easier. And then final answer, genotype. Okay, so looking at it, it's 25%, 25% for each. It's missing a T here. And then for the phenotype, right, 25%. For the first one here is big G, so it's gray, gray and long, gray, long. Second one, 25% gray, short. Next one, 25% white, long. And the next one, 25% white, short. And that's it. Okay? That's that's all you have to do for 5 marks. So I will allocate the time appropriately for you, because I know it takes time to write out and then to type it in. Um, it shouldn't be a problem. You shouldn't run out of time. Is it clear what I expect you to do for the quiz number 4? You're not gonna have like 5, 6, 7 of these questions, okay? Like you're just gonna have some of these questions. The rest of the quiz will be like regular stuff, like multiple choice and things that you've been doing all along. Okay? I certainly hope so. Like I said, please practice typing it out. If you're doing it for the first time, when it's the actual quiz, you're gonna have trouble. Okay, you're gonna be yelling at the screen, and I don't want that. Okay, let's do another example. This is example 5. Okay, assume curly hair is dominant to straight hair, and this is a nice question because the alphabets are already chosen for you. You don't even have to think too much. Albinism is a condition in which cells which normally produces pigment does not do so. A person with this condition is called an albino. The ideal for skin albinism is small n, and for normal is big N. Okay, so basically, an albino is someone who has very pale skin color, right? Blonde hair, blue eyes, who otherwise normally would not look like that. Okay, and so here we have the woman, a woman with curly hair and albinism, and then we have the man with straight hair and normal skin. So let's try to put it in a Punnett square to show the relationship, it's a little bit easier that way. So there we go. Circle is female, square is male. They're gonna have kids together. And the child has straight hair and is albino. So like if you don't know the gender of the child because the question didn't tell you, you can use diamond. Yeah, that's what it is. So here the woman has curly hair, and curly hair is dominant, which means she's gonna have a capital C. But I don't know what the other one is. The other one can be big C, or like big C, small c, right? Both are going to be possible genotypes for curly hair. So I'm just gonna leave it as it is for now. The woman has albinism, which means she is going to be little n, little n. As for the man has straight hair. The only way to have straight hair is for him to be homozygous, little c, and he has normal skin. So capital N for sure. But again, I don't know if he's homozygous, big N, or heterozygous, big N, small n. Right? We don't have that information yet. Okay, what about the child? What about the child? The child has straight hair. Straight hair is little c, and he's an albino, which means is little n, little n. Right? So that's all we know. Now we're gonna ask ourselves, where did the child get the little c from? Well, one of the little c's is from the father for sure, which means the other one has to come from the mother. Right? So now we know the mother is heterozygous for the hair. And similarly, one of the little n is gonna be from the mother, which means the other little n must be from the father. Okay? So that's how we can use different people in the family tree to figure out the missing information for certain people. All right? All right. Let's do concept check question. Consider the cross, right, of this and this. What is the probability of producing a genotype of that? So this is a little bit harder now because it's three genes, right? Tri-hybrid cross, if you would. We are not gonna do a Punnett square, right? If you do a Punnett square, it's gonna be super big. How many gametes can this person produce? How many different types of gametes? Do you remember how to figure that out?
3.
There are three genes, but how many gametes?
2, 2, 2.
Two, two, two. And then what do you do with those twos?
Multiply.
That's right. So look, there are two possibilities for gene A, two possibilities for gene B, and two possibilities for gene C, which means there are eight possible gametes. Right? Same thing here, eight possible gametes. If I do the Punnett square, it will be 64 different combinations, right? And it's too much work. You're not going to be able to, do that within the constraint of the time limit. So how do we do this question? Well, it turns out we can actually focus on each one individually. Okay, so let's say we look at gene A first. Okay, so gene A, we would have big A, small a on one side and big A, small a on the other side. And we can go ahead and do the regular Punnett square. Okay, you should be familiar with this already. We learned it on Monday, and I asked you to practice. So what does the question want? The question wants us to calculate the probability of producing big A, big A. Okay, so looking at this, what's the chance of producing big A, big A? Well, there is big A. And the probability of that happening is 25%. Okay, but these are in fractions, so I'm going to do fractions, 1/4. Now you can repeat the process, just change all the A's to B's, right, and change all the A's to C's, and then you will be able to figure out these ones as well. So the probability for the first one is 1/4 times, second one is also 1/4, and then also times 1/4. So that's going to be 1/64. That's the answer. I'm going to give you a question to try. All right, so let's say we have A. Okay. Go ahead, work it out. We'll take it up in 2 minutes. All right, that was 2 minutes. I got some answers coming in, but I haven't done it yet, so I don't know what the right answer is. Anyone else feel like sharing their answers before we take this up? Or are we all very confused? Hmm. Okay, so we're gonna do the A's first. A is gonna be big A, small a, and big A like that. And we just fill it in like normally. And they want us to find big A, small a, which is, what's the fraction? What's the percentage?
2/4.
50%.
Yeah, 2/4 or 1/2, right? 50%. We'll just keep it as fraction. Okay, it's easier that way. Okay, then we're gonna do the B's. B's are these ones, which is big B, and then small b. And if we go ahead and fill in the Punnett square, what is the probability of getting small b, small b?
1/2.
1/2 again.
Yeah, 1/2 again. That's it. And then big C, and small c, small c. Even without the Punnett square, I'm hoping some of you might be.
100%.
That's right. What's 100% in a fraction?
1.
That's it, 1. And we have a bunch of numbers, and if we don't know what to do in biology, what's the most common likely operation? What are we going to do with them?
1/4.
Yeah, we're going to multiply them together. That's right. Okay, so half times 1, it's 1/4. So the answer is 1/4, okay, or 25% chance. All right? So if you have more than 2 trays and you need to keep track of things, you just do them separately and then multiply the probabilities together. Okay? Questions? Okay, I'm gonna let you try another one here. Okay, please go ahead. Uh, if you find yourself in a situation where you're doing the big, 16 boxes Punnett square, you are not doing it right. Right? So I'll let you try first, okay? A couple minutes. Okay, let's take it up. All right, so something like this is definitely possible on that quiz, okay, or end test. It says two true breeding. True breeding means it is pure. Okay, we talked about this before. True breeding means pure. And there are peat plants. One is red and axial flowers. Again, you don't have to know what it means. Okay, red is the color. Axial means like the position of the flowers. Okay, so it's red and axial, and then the other one is white and terminal. Right. So here we have red and white, and then we have something called axial and terminal. But the question does not tell us explicitly which one is dominant, right? So how do we tell? Well, it says here, all F1 individual have red axial flowers. Okay? All F1 individuals have red and axial flowers. Remember, if the parents are both pure, then the dominant trait will show up in 100% of the F1. And since all of them are red, then red is dominant over white, and axial is dominant over terminal. So you can use capital R for red, and then lowercase r for white, capital A for axial, and little a for terminal. Okay? So that means all the F1s are 100% big R, small r, big A, small a. This is the situation where we need to do the 4x4 Punnett square, right? With 16 different combinations, but you're not supposed to write it out. Anytime you have to do the 16 different possible combinations, you have to remember the ratio. Does anybody remember the key ratio, the four numbers for the ratio?
9:3:3:1.
That's right, 9331. A 9331. And what are we looking for here? We are looking for red and terminal. So red is dominant and terminal is recessive. Okay, dominant. And this is recessive, which means I am looking for one of these things. Dominant, recessive. It is 3 out of 16. And we are having 1,000 of these flowers. And so you go ahead and you key it in. 3,000 divided by 16, which is 187.5. Okay. And so you choose a number that's closest to it, 190. Okay. It's not going to be exactly 187.5, so you would find the closest number. Right? Well, so many typos in this question. Approximately. Approximately how many of them? Anybody have any questions? You have to know how to do these. Otherwise, it's gonna be very difficult, the quiz. Okay. Well, like I said, there are more practice questions in the study guide, so please check them out. All right, we have a few other concepts we have to learn, so here we go. I'm just gonna do it over here. It's easier for you for us to see. Not everything is dominant and recessive. Okay, it turns out the interaction of alleles can be more complicated than simple dominant and recessive. Okay, in some situations we can have what's called codominance, and in other instances we can have what's called incomplete dominance. Okay, it's easier if I just give you examples to help you understand rather than writing out the definition. So for everything we've done so far is dominant and recessive. You either have the dominant trait or you have the recessive trait. But for some situations, it's codominant, and the question will tell you that it's codominant, so you don't have to guess, which one it is. So for codominance, what that means is you will have one allele, let's say big R, and if you have two of them, then it's gonna be like red flower. Okay, and then two little one is going to be white flower. And then normally, if it's just dominant and recessive relationship, the big R, small r would be also red, right? But in the case of codominant, it would be red plus white. Both would show up. A codominance inheritance pattern is where the allele is not going to be able to cover up each other, and it ends up both showing up together. Right? So I'll write that down for you. Both alleles are expressed in the heterozygous um, genotype. Okay. I guess, for the heterozygous genotype. And sometimes, instead of both showing up, it's going to be in the middle, a blend of the two alleles. So that we call incomplete dominance. So again, big R is red flower. Small r is white flower. And then it's not red, it's not white, is somewhere in between. So you get pink flower. Right, so this one is an intermediate blend of both alleles for the heterozygous genotype. All right. So I'm gonna give you an example. Let's say we have a cat. Okay, cat with long tail, and then we have a cat with no tail. And then we have a cat. They get worse and worse when I draw them. We have one with short tail. Okay. So for the tail length, based on this display, do you think this is dominant recessive, codominant, or incomplete dominant? Let me give you a poll. Okay. What kind of
Which one you said?
yeah, I'm gonna write out for you. Do you think it is A, just basic dominant and recessive, or do you think it's codominant, or do you think it's incomplete dominant? Right? We have long tail, short tail, and no tail. Right? What is going on here? All right, that was a minute. Yes, this would be incomplete dominance because short tail is an intermediate, right? Like a middle version of long tail and no tail. You're gonna get short tail. It's not codominance. Codominance means both have to show up, right? Okay, both have to show up. In this case, that's not what happens. Okay, I'm gonna try one more with you. All right, let's say we have one person. Uh, type A blood, And then we have another person, type B blood, and then their kid. Their kid has type AB blood. What kind of relationship do you think blood type inheritance follow? Is it dominant recessive, codominance, incomplete dominance? Excellent. Almost everybody answered, and everybody who answered got it right. This is codominant. Very good. Okay, moving on. I'm just gonna delete that. Let's do a question. In snapdragons, red flower color is incomplete dominant over white. Right, so like I said, the question is gonna have to tell you. The heterozygous condition produces pink flowers. What will be the result of a cross between two pink flower snapdragons? Right, so it's probably a good idea to write down all the genotype first. So big R is red. I mean, it could be white, like it doesn't really matter. It's up to you, right? There's no more dominant and recessive, and this is white and this is pink. How do I know this is pink? Well, the question says so. Heterozygous condition produces pink flowers. Okay. What will be the result if you cross a pink with a pink? Do it. Do the Punnett square and let me know. What do we have? Anybody? Okay.
50% pink.
50% pink. And what about the other ones?
Red and white.
And the percentage for them?
Yeah.
25?
Yeah, very good. Okay, so big R, small r on the side, big R, small r at the top, and then we're gonna do the Punnett square, okay? Big R and small r and small r. So over here, it is going to be, these are red, right? These are red. Okay, so 25% red, 25% red. And these ones are pink. I remember that's why it's important to write down at the beginning so you don't get confused what the genotypes turn out to look like. Okay. 50% pink and then 25% white. Okay. Here. Are we together? I hope so. You can ask anything if you don't understand. All right. We are almost there, huh? This is week 11. Just 3 more weeks. And that is it. You can do it. A red bull is like male cow, crossed with a white cow produces a roan calf. The roan calf has intermingled white and red hair. That's a roan calf right there. Okay? It's co-dominance, okay? Both kind of hairs. If a roan bull is crossed with a white cow, what percent of the calves would be roan? So here we go. We can write out again. Big R, big R. Big R is red. And then big R, small r is something called roan. Small r is white. Right? It's basically the same situation as the previous question, but this time we are taking a roan bull. Roan bull is big R, small r, and we're crossing it with a white cow. So we can put big R, small r across the top. You could do it on the side. It's not going to affect your answer. And we fill in the Punnett square. Big R, small r, small r, small r. And we can see 50% will be roan. Okay, it's only asking you for the roans. There we go. Okay. What if I want only roan bulls? What kind of parents do I need to guarantee 100% roan calves? Let me repeat the question. If I want 100% roan, what must be the parents?
Red.
Red and what?
Red and brown.
Red and roan? Okay, so
I'm
let's try.
confused.
That's okay. Let's
Red.
try red and roan. Yeah, sure. Go ahead. Do you have another suggestion? Lisa?
Red and white.
Red and white. Okay, so let's try it out.
100%.
Yeah, so this is red and roan. If we do red and roan, and this is red and roan. Okay, so again, you fill it in like that. Only 50% roan, right? You see? Let's try red and white. If we do red and white, what's going to happen? 100% roan.
Mhm.
Okay, which is interesting because sometimes people think, okay, if I want 100% pink flower, then maybe I start with pink and pink. Not necessarily. Okay. If you want 100% red cow, what must the parents be? 100% red. What must the parents be?
Red.
Red and what?
Mm, red and red.
That's right. Red and red would equals to 100% red. Right? This is big R, cross big R, 100% big R, big R. All right. So when you're studying, try to think about these different combinations. All right. Okay. Moving on. Next, I'm gonna go through the PowerPoint slides with you. This is the second last thing we're gonna learn. Sex-linked conditions. So most of the things we talked about so far is transmitted through the autosomes, chromosome 1 to 22. But some conditions, some traits are found on the sex chromosome, either X or Y, and we call these sex-linked conditions. Okay. So some example of sex-linked conditions is specifically like X-linked conditions. X-linked means it's carried on the X chromosomes, include hemophilia, which is a bleeding disorder. Your blood don't clot. If you have a cut, keeps on bleeding. It doesn't stop easily. Color blindness, that's another X-linked conditions. If it's Y-linked condition, then only males can get it. Okay? Only males have the Y chromosomes, right? Okay. But if it's X-linked, it can affect both males and females. Okay? And depending whether it is X-linked dominant or X-linked recessive, it could affect more males or it could affect more females. I'll explain in a second. So we'll use color blindness as an example, okay? What number do you see? Let's do a poll. Don't tell me. What number do you see? If you see 74, choose A. If you see 21, choose B. If you don't see any numbers, then we have a big problem. Okay. If you see 74, choose A. If you see 21, choose B.
What if you see both?
You see both? Very nice. Okay. Interesting. What's the first number you see? I guess that's a better way of asking. Yeah. Okay, so people who do not have red-green color blindness, they would see the number 74. If you don't see 74, if you only see 21, then you probably have color blindness, which I'm sure you would already know. You don't need your biology teacher to tell you that. So this is called the Ishihara test. Right? It reviews if people have a particular kind of color blindness. Okay? And that is an X-linked condition, okay, which is transmitted through the X chromosome.
If I see 74, what was mean?
It means you have normal vision.
Okay.
Congratulations. Yeah.
Thank you.
All right. So we're gonna
Yeah, sir, one doctor told me I have color vision for green, but I can see green. I don't know why he told me.
yes, no, I mean like there are different kinds of color blindness though. Okay. Like so this particular test only tests for red-green color blindness where people have trouble telling apart red and green. But there are other kinds of color blindness that could exist as well.
He
So
told me for green, but here I
just
can see
green,
green.
yeah.
Yeah,
But you're able to see green,
yeah,
yeah. But here's the thing, right? Here's the interesting thing. If a person is colorblind to green, then all their life they would associate that shade, like they would associate the color green with something. So like they might not know that they're not able to see green. You know what I mean?
yeah.
I'm just saying, okay, let's say for the person who cannot see green, green appears as, I don't know, purple to them. Then they would think that is green, right? And they wouldn't
Yes,
know they
that's why I told you that he told me I'm
yeah.
colorblind. But here it's one type of proof that I can see green.
Right. So sometimes, there might be additional tests that are
Yeah.
required. Yeah. Okay, so we're gonna take a note here on color blindness and X-linked condition in general. Okay, but I'm just gonna use color blindness as an example because it's easier for people to um, comprehend, I guess. Whereas something like hemophilia, it's like, well, what is that? Like, I never heard of it, right? Okay, but it's the same concept, right? So color blindness. All right, we're gonna draw. Oh, so first of all, color blindness is an X-linked recessive condition. Okay. Uh, so just to go through this again, this is a man, and what sex chromosome does a man have?
XY.
Mm-hmm. XY, XY. So if this person has normal color vision, then there is nothing wrong with his X. The X is just regular X. Okay. Now, if someone has color blindness, we're gonna shade him in. Okay. Again, it doesn't like you can shade boxes in different pedigrees. They don't necessarily all means color blindness. We are talking about color blindness right now, so that's why shade in means color blindness. Last class we were talking about a long nose, if you remember, and anyone who got shade in has a long nose. Like shade in just means they have the trait that you are interested in. In this case, is color blindness. So the person is X C. We can use any superscript. I'm just gonna use C for color blindness. Y. So this is a colorblind male. This is a normal vision male. And so you see, male is a little bit of a disadvantage here if we have if we're talking about a recessive condition. Okay, this part is important. Pay attention. Okay, if we're talking about X-linked recessive condition, then generally affects more male than female. Why? Because men only have one X. If we got the disease X, if we got the allele, if we got the X with the colorblind allele, then immediately we'll be colorblind. But what about female? Well, let's see. This is XX, normal vision, female. And how about this? How about this? Oh, how about this? What does this mean? And what's the genotype? Help me out. What should I write for the genotype of the woman?
XX
Is it XX again? Yeah.
and C.
And
Colorblind.
and the C for both of them. That's right. So this would be a colorblind female. Okay. Both X's has to be the colorblind uh, allele in order for the woman to be colorblind. What about this one? XXC. Are they colorblind or not colorblind?
Not
Not colorblind? Anyone else? Let's do a poll.
recessive.
If you think they're colorblind, choose A. If you think she's normal, B. Colorblind, normal. What's going on with this lady? Remember, this is an X-linked recessive condition. Okay, very good. This is going to be a normal vision. Normal vision, female. Okay, but she's a carrier. Okay? For carrier, we shade in half. Carrier. Carrier means she has the colorblind allele, but she's not going to have the color blindness because she has a normal X chromosome, which will cover up the disease allele, right? So it's recessive, the color blindness. That's why a normal X is able to cover it up. And that, again, is why recessive X-linked conditions will affect more males than females. More males than females. Because male, you get one bad X, that's it, you're gonna have the disease. For females, you need to have two copies in order for the disease to show up. Okay? Now listen carefully. I'll write this down for you later on. What if it's X-linked dominant? If it's X-linked dominant, do you think it affects more male than females? They're going to affect them both the same or affect more female than male. Okay, we're talking about X-linked dominant now. Let's think about that for a second. Who's going to get affected more if it's X-linked dominant? Okay. Anyone else? Okay, so with male, with both. Okay, well, actually,
Both.
both, yeah. Well, if it's X-linked dominant, female is worse off. Okay, because female has two X's. And so like the X, instead of being protective here in recessive, in the case of dominant, the X is more like a liability, right? Think about it. Women has to inherit two X's. Okay, so if you inherit more X's, there's a greater chance you're gonna inherit a mutated one, right? For men, we only have one X. So if it's X-linked dominant, it affects more female than male. Okay. All right. Enough of that. Let's do some practice question. Determine the expected outcome for the following process. Okay. Now on the test, if you have to do these, you can just go XC like that, XCY. You don't have to do the superscript. Okay. Like it's fine. All right. Okay, so here we have a carrier female and a normal male. Let's do this one first. Carrier female is XCX, okay, or XXC. It doesn't matter where you put the C, okay? It's carrier female. And then normal male. Normal male is XY. So we're gonna go ahead and set up our Punnett square. So XX here, XY, XXC, XCY. Okay, so what's gonna happen here if is a girl? Oops. If it's a girl, are they gonna be colorblind? Anybody colorblind in this family for the girls?
No,
No.
only carrier.
That's right. 100% normal vision. 100% normal vision. No problem. But if it's the boys, these are the boys. Okay. Now we're only looking at the boys alone. Okay? If you look at the boys, then 50% boys normal vision and 50% of the boys will be colorblind. Okay, so we're not looking at kids in general. Okay, we're looking at like girls versus boy. If we look at kids in general, then only 25% chance. Right? Only 25% chance of a colorblind child. Okay. So if you look at the boys and the girls separately, then it's only 2 boxes at a time. But if you look at kids in general, then it's 4 boxes. Okay, why don't I give you a moment to try the next one? We have normal male with a colorblind female. Normal male with a colorblind female? All right, so here normal male is XY, colorblind female is XCXC, and we're gonna do the
All are
Punnett square.
colorblind.
Was that all of them are colorblind?
Yeah.
Yeah, poor kids. Let's see if you're right.
50% male colorblind.
Yeah. Okay, let's find out. So we're gonna have XXC, XXC here, and then for over here. All right, so let's look at the girls. Are the girls going to be okay? Looks like it. Right? The
Cards.
girl. Mhm.
Oh, yeah, yeah.
Here are the girls. They will be
This
okay.
is it. Huh?
Yeah, they're okay. They're all carriers, but they don't have color blindness. 100% normal vision. Okay, and then for the boys, 100% colorblind. Okay, boys, girls. Okay, so you have to understand for X-linked conditions, the boys always inherited from the mother. The father can never pass on an X-linked recessive condition to the boys. They can pass it to the girls, but they cannot pass it to the boys. Think about that. Okay? How do you have a boy? What do you pass as a father? What do you need to pass on to make a boy? Which chromosome does the father have to pass on to make a boy?
Why?
Y, that's right. And if it's an X-linked condition, you are not gonna transmit it to the sons. You understand? That's a key point to remember. Okay, there are two more. I'm sure you can try it yourself. The next thing is gonna be very confusing, okay? There are only a few questions of these on the quiz, but nevertheless, it's confusing. Before we move on, do you have any questions you want me to answer? Anything you need me to clarify? Now is the time. You guys never have questions. But yeah, you know what? I think you guys are good class, right? You guys have been coming to class consistently. I think we have the same number as the first week of school. So that's really good thing. Um, can I repeat the last part I said about important? Oh, what's important is that for X-linked conditions, an affected father can only pass it to the. Okay, someone finish the sentence for me. Let's see who else was listening. Can for an X-linked condition, an affected father can only pass it to who?
Female.
To the daughters. That's right.
Daughter, yeah.
Yeah.
Mhm.
And never the son. Never the son. Right. There you go. All right. I know you don't have these slides, but I'll post it for you afterwards. Okay. We're gonna study a few pedigrees and we're gonna try to figure out what kind of inheritance pattern it is. Okay. Just give me a second. We did a little bit earlier already in the PowerPoint slides, but I have a few more here. It's coming. Everything is so slow. No, what did I do? Okay, here we go. Now previously, oh, that's not what I want. Previously, we were just trying to figure out whether it's dominant or recessive. But now we learn about X-linked. We have to figure out whether it is autosomal or X-linked recessive or dominant. Okay, so let's take a look here. What do we see? Well, first of all, we see that uh, there is generation skipping. Okay, look at this family here. This side of the family tree. Nobody has it here, and then someone has it, and then it disappears again. And so this is called generation skipping. Okay, so I'm gonna write out for you. Skips generation. If you see something that skips generation, it's likely to be recessive. Likely to be recessive. Okay, so that's hint number one. What's another clue here that it might be recessive? We talked about it on Monday. Let's see if anybody remember. The child has it, but what? There needs to be a but in that statement. But the parents do not. That's right. Look, these people don't have it, but then the kids do. Right? So both, you can say two unaffected parents have,
Parents are heterogeneous. That's it.
yeah, exactly. They're both heterogeneous. Yeah, has an affected child, right? So that's also recessive. So based on these two clues, generation skipping and the parents don't have it, but the kid has it, that tells me it is recessive. Okay? But then is it X-linked or is it autosomal? Is it X-linked or is it autosomal? Okay, so
Autosomal?
and how do you know that?
Because the parents doesn't have it, so I guess
Okay.
like that.
Oh, yeah, but if the parents don't have it and the kid have it, that only tells you it's recessive. It's not definitive whether it is autosomal or if it's sex-linked. Okay. Now hold on. Let me just circle this guy back here. It's getting a little bit messy here. So a couple more hints here. Look, we have more males than female, okay, as opposed to equal male and female. So that suggests it might be X-linked, but it's not definitive yet. Okay, it's not definitive. Okay. But the really definitive thing here to see is we have an affected father, and the affected father passed it on to the daughter, right? But not the son. And over here, we have an affected son, okay? And where did the affected son get the disease from? Well, it's not from the father, but it's from probably from the mother. Okay? The mother here is going to be a carrier, and you can see again the father here did not pass it on to any of the son. Right? So more males than females, and at least based on the information I have here, father to son did not happen, but we see father to daughter happening. Okay. So based on these, I'm going to say it is X-linked. Okay. So this would be an X-linked recessive condition. Whereas if it was supposed to be autosomal, then I probably would see equal number of males and females affected, and I would probably see the affected male passing on to both females and males. Now, is this definitive? No, but if I have to uh, say one way or the other, I'm more inclined to say it is X-linked recessive. Okay, we're gonna try a few more. Again, I'm gonna post this online for you, and you will practice with them. Okay, this one. Okay, first of all, we want to figure out if it's dominant or if it's recessive. Okay, do we see skipping of generations here? Anybody skipping?
No.
No skipping, right? Each generation has people affected. Okay, so no skipping. If I don't see skipping, I am inclined to say it is dominant. Okay, I'm inclined to say it is dominant. Right? We don't have one of those definitive cases where both parents are affected, but the child is not. But just based on the number of people who are affected in the entire family, it's likely it is dominant. Okay, more people affected. Now, how many males? One, two, three, four. Four males, three females. You can say more males than females. Okay. But the real thing that tells me this is not X-linked is the fact that son to son transmission, right? Sorry, not son to son, father to son, father to son. Is father to son possible for X-linked? What did I say earlier? Father to son is not possible, right? Yeah, so
Yeah.
that means this must be autosomal. Autosomal dominant. I know it's a lot to take in, but
So, when it comes from father to
Mhm.
son, this is autosomal, and when it comes from mother to son, this is sexual.
Okay,
Something
yeah,
like that.
yeah. So if you see father to son, then it's definitely not X-linked. Okay,
This is, yeah,
right.
autosomal.
Is if you see father to son, then it is definitely not X-linked. Okay, not X-linked. But if you see mother to son, I cannot say whether it's X-linked or not, like definitively. I have to rely on other clues. All right. Okay, we're gonna do another one here. We're gonna do another one. Okay, I'm gonna let you think about it for a second. Okay, so first of all, you gotta figure out whether it's dominant or recessive first, and then you're gonna have to figure out whether it's X-linked or not. All right, anybody? Any brave soul? Do you think this is dominant or recessive, and how do you know?
Dominant, no skipping.
No skipping? Anyone else?
Recessive because number three, this is not any.
Yeah, so like when you see skipping or not skipping, you cannot just look at the whole tree. You have to look at like sections of it. Look, that's basically one family right there, right? That's one family. Uh, this would be actually, you know what? This over here, this would be like another branch of the family, right? So you see, it actually has skipping over here, right? No one has it, and then has it, and then no one has it. So there is a little bit of skipping going on there. And even with this side, I would still call that skipping. Skipping doesn't have to be like alternating generation, but it could be like no one here, and then someone has it, someone has it. So based on that, this is definitely recessive. Okay, recessive because of skipping, and also because of this. Okay, because of this. Look, two parents don't have it, and the kid has it. That's recessive, right? That's recessive. Now, do you think this is autosomal? I'm gonna do the poll here. Okay, if you think it's autosomal, please choose A. If you think it's X-linked, please choose B. If you are super confused, you can choose C. Autosomal A, X-linked B.
Sorry, can you repeat autosomal A or B?
Yeah, autosomal is A.
Okay, thank you.
Yeah. All right, we have 50-50 here. Half of you say is autosomal, half of you say is X-linked. But look at the last question, please. The last question. Father to son. If you see father to son, then it is definitely not X-linked. Do you see father to son here? I do. Father to son,
Yes, yeah.
right? Which is definitely not X-linked. So this is autosomal. All right. Okay, we're gonna do more. We're gonna do more. Okay, let's see this guy. All right, what do you think here? All right, just take your time. All right, I have 6 answers, 7 answers. Anyone else? Okay. I I uh I have answers all over the place. let me share the results and you can see. Basically, everybody chose one of the answers here. All right, let me break this down a little bit for you. Okay, let's try again. Okay, I'm gonna relaunch the poll. Okay, let's try to figure this out first. Okay, never mind these. Okay, do you see this as skip or no skip? Okay, let's do the poll. Based on this, do you think the tray is skipping generations or not skipping generations? Skipping means it doesn't show up in every generation within like a branch. Okay, no skipping means it shows up like there is someone having it in every generation. So do you think this is skipping or no skipping? Okay. Anyone else before I review the answer? All right, most of you got it right. This is skipping. Look, focus on one side of the branch, like over here. Look here. You, you, you're not necessarily looking at the entire pedigree, okay? So this is one branch of the family, right? See, someone has it, and then no one has it, and then someone has it, right? That's skipping. That's skipping. If it skips, then is it dominant or is it recessive?
Recessive.
Recessive, right? So it's either going to be this one or this one. And more importantly, what is the giveaway? You see this thing in the pedigree, guaranteed to be recessive. It's something like this. Parents don't have it, but the kids do. Okay? If the skipping things confuse you, then you look for this. This is the dead giveaway that is recessive. Okay? Dominant is not possible to have this kind of pattern. Right? Dominant means there is like a big R somewhere, and the big R has to come from the parents. If the parents have the big R, they have the disease as well. Right? So dominant is not possible in this case. Okay, so is it autosomal or is this X-linked? Okay. So how do we know? How do we know definitely not X-linked? Definitely not X-linked is father to son, right? Do we see father to son here?
No.
No father, yeah, no father to son. So is is not definitely not X-linked. It could be X-linked, in other words, it could be X-linked. Okay. So finally, how do we know if it's X-linked or autosomal? Remember, we know it's recessive already. If it's X-linked recessive, okay, backtrack. What did Vincent say? X-linked recessive affects more male than females. Okay, affects more male than female. And if you look at this, it surely does look like a lot more males has it than the female. Okay, so more males affected than females. Okay, so it is going to be X-linked recessive. Okay, whereas if you see roughly equal number of males and females, then it's going to be autosomal. Okay, autosomal.
And autosomal comes from father.
Autosomal can be both father or mother. Right? There's no restriction.
Okay.
Okay. All right. Are you throwing things at the screen yet? Hopefully not. I have one more for you. Okay, I have one more for you. And I mean we can do more if you guys want, but I feel like you already, you know, not liking this too much. Okay, what is this one? This one is tricky. I mean, it can be tricky. It might not be tricky. I don't know. You tell me. Okay, you tell me what's so fishy about this thing. Okay, let's call it a bonus question. Bonus. How is this different from like all the ones we've seen so far? Like, what's one thing that really stands out to you, if any? All males, that's right. Only guys have this thing, right? And it's like all the guys. And more importantly, if the father has it, all the sons will have it, and all subsequent sons of the affected son will also have it. And if these men go on and have more sons, you bet they're gonna have it too. Okay? So what kind of conditions exclusively affect men? Do you know the answer? It's not X-linked, is it?
It's not, I
It's
think.
linked recessive.
Is it's okay, but linked to what though?
Recessive.
No, what chromosome is it linked to?
Autosomal?
Autosomal.
No, no, no. Y link, that's right.
Why? Yeah.
Yeah, someone private message me. Don't private message me when you have the right answer. Tell the whole class. Y linked. This is Y linked because only guys have it, right? It's on the Y chromosome. That's why all the males, all the affected males have it. Okay? And we don't have to say dominant or recessive because there's only one Y. If you have one Y and it's the disease Y, then you're gonna have the condition. Never mind whether it's dominant or recessive, right? Dominant recessive doesn't even apply. It only applies in a situation where you have two copies of the chromosome, right? Okay? Just one last one, I promise, and then I'm gonna be quiet and let you go. Over here, okay, try it one more time. Don't freak out. There are only like 2 or 3 questions like these on the quiz. It's not gonna be detrimental if you get it wrong, but do try to understand. Okay? Go and figure this one out. Okay, it's almost been 2 minutes, and looks like people are still confused. I think it's a tough thing, I guess. Okay, let me walk you through one more time. Right? Do you think this skips or no skip? Skip or no skip? Right? That's the first thing you want to ask yourself. Skipping or no skipping? Well, if you look at this family tree here, that's no skip. Everybody has it. There's someone who has it in every generation. If you look at the middle, yeah, it looks like it skips, right? There's in the beginning, but then like it's gone. But then if you look at the right family here, the right side, then no skips, right? So in general, it looks like it's not skipping more than skipping. So I'm gonna say not skipping. Not skipping. If it's not skipping, then it's dominant. Right? If it's not skipping, then it's dominant. Another thing to look for is we can see affected parents always have sorry, you can see parents who are affected also have affected kids, right? So that's another sign that it is going to be dominant. Now we have to figure out whether this is X-linked or whether it's autosomal. So again,
Daughters are more affected.
sorry, what's that?
Daughters are more affected, so
Are they though? More females affected than males? Yeah. Oh, it seems that way. But then we look for the the giveaway, right? If you see father to son, then it cannot be. It cannot be.
Autism.
Yeah, but then like we actually don't really know here because you can see, it could be mother to son. We can't really say 100% is from the father here. And over here again, we can see, you know, we 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 have both parents who are affected. So how do you call this one? Well, in the end, we can see that there are more females, definitely way more females than males. And we know in dominant X-linked, that's the case. So we're going to say that this is X-linked dominant. Okay, X-linked dominant, more female than males. Okay, so the correct answer is C. All right. So that's it. There are plenty of examples here. You can go through them all and try to make sense of it. Um, Feel free to email me if you need further clarification. Other than that, that's it for today. We will do lecture 9 next week. Right? Please print the stuff. Right? It's really complicated, lecture 9. See you then. Bye-bye.
Yeah, bye-bye.